Hey Amanda, so I'm going to start off with the first Edulastic assignment, which is the easy one. So here we have a bunch of definitions. We're going to see which one of these definitions matches with the appropriate theorem. So what I like to do is I just read the definition and then match it here. So it says here for this first one, if corresponding angles are congruent, then the two lines are parallel. So normally we start off when we're trying to get the theorems regarding angles, you are given if the angles are parallel, then corresponding angles are congruent. So which is the other way around of what we see here. So that would be the converse. Okay, so normally we show parallel lines and then angles are congruent. So if you have it the other way around, where if the angles are congruent, then the lines are parallel, this is the converse of corresponding angles postulate. See corresponding angles, corresponding angles. If two parallel lines are intersected by a transversal line, then corresponding angles are congruent. So this is what I just said. This is the original one where you have parallel lines and then the angles are congruent. So this is corresponding angles, so that goes with the corresponding angles postulate. If two parallel lines are intersected by a transversal line, then the consecutive interior angles are supplementary. So this is consecutive interior, so I'm going to look for consecutive interior, and that's the regular one, not the converse. So that would be this one here. If consecutive interior angles are supplementary, then the two lines are parallel. So this is the other way around. So this is the converse of the consecutive interior angles. If A is equidistant to the endpoints of line segment BC, then A lies on the perpendicular bisector of the line segment BC. So let's see what that could be. These are all angles, so no. Perpendicular bisector, converse of perpendicular bisector. It's either going to be one of these two here, because these are the only ones with the perpendicular bisector. So you see how it says then A lies on the perpendicular bisector? I'm not sure. I'm going to leave this one for later and then see if we can decide. If two parallel lines are intersected by a transversal line, then alternate interior angles are congruent. So this is parallel lines first and then the angles. So this is the alternate exterior angle theorem, which is this one here. The sum of the smaller sides of a triangle must be longer than the longest side. So that is the triangle inequality theorem. So where is it? The triangle inequality theorem states that it uses inequalities, right? So that's where you would set up the longest side and it would have to be greater than the sum of the other two sides. So that's why it's called the triangle inequality, because you would use the greater than symbol. So this is the last one there. If two parallel lines are intersected by a transversal line, then alternate interior angles are congruent. So alternate interior angles came after, so this is the alternate interior angles theorem. Then this would be the converse, because this is giving you that the angles are already congruent and then the lines are parallel, so this is the converse of the alternate interior angles. Same thing here, if alternate exterior angles are congruent, then the lines are parallel. This is the converse. Then here, mid-segments of triangles are parallel to half the length of the remaining side. So that can only be the triangle mid-segment theorem, since it's the theorem names kind of tell you what it's about. So triangle mid-segment has to be this one. Then finally, if point A is on the perpendicular bisector of the line segment BC, then A is equidistant to B and C. So this must be the converse, because, I'm sorry, this must be the perpendicular bisector theorem. And that's because it's telling you that we have the perpendicular bisector, therefore this happens. It's kind of like the same thing here. Alternate exterior angles, you have to be given that you have parallel lines and then the alternate exterior angles. So you know what, let me just double check with Delamo. Okay, so here we go. I figured it out. So here, if you are given that the point A is on the perpendicular bisector, and then that means that the point is equidistant to B and C, then that is the perpendicular bisector theorem. So this is how you can know. If you know it's a perpendicular bisector, it is told to you, then that is a perpendicular bisector theorem. However, if it's the other way around, or you're given the point and then it must be on the perpendicular bisector, that is the converse. Okay, let's go on to the next question. Which of the following sets of lengths could form the sides of a triangle? So for this is the triangle mid-segment theorem. So I'm going to pull this up here so we can kind of work it out. So if you, the triangle inequality theorem, the triangle inequality theorem states that if you were to add two of the sides together and then compare it to the third side, it has to be greater than that third side. So you have to kind of do a little bit of work here. So we have 5, 9, and 7. So 5 plus 9 has to be greater than 7, which it is. So then we continue with the other sides. We just do all the different versions. So 5 plus 7 has to be greater than 9, which is true. And then lastly, 9 plus 7 has to be greater than 5, also true. So this one is a triangle. Now here we have 4, 8, and 3. So 4 plus 8 has to be greater than 3, true. 4 plus 3 has to be greater than 8, which is not true since 4 plus 3 is 7 and 7 is not greater than 8. So that would not be a triangle. Then we have here 11, 11, and 22. So 11 plus 11 has to be greater than 22, which 11 plus 11 is 22. 22 is not greater than 22, so this is not a triangle. Then we have 2, 5, and 4. So 2 plus 5 has to be greater than 4. True. 2 plus 4 has to be greater than 5. Also true. And finally, 5 plus 4 has to be greater than 2, which is true. So this one here works. Then we have 7, 9, and 12. So 7 plus 9 has to be greater than 12. True. 7 plus 12 has to be greater than 9. Also true. And finally, 9 plus 12 has to be greater than 7. True. So this one would also be a triangle. Last one is 10, 8, and 2. So 10 plus 8 is greater than 2, which is true. 10 plus 2 has to be greater than 8. Also true. And then 2 plus 8 has to be greater than 10. But 2 plus 8 is 10. It's not greater than 10. So not true. So the only triangles, or the only lengths here that are triangles are 5, 9, 7, 2, 5, 4, and 7, 9, 12. Quadrilateral ABCD is shown. For what value of x will line BD be the perpendicular bisector of segment AC? So BD, perpendicular bisector of AC. In order for those segments to be perpendicular bisectors, the quadrilateral could be one of three things: either a square, a rhombus, or a kite. Now this is not a square because it's not a square, right? I mean, it's obvious. It's not necessarily a rhombus because if it was, then the perpendicular bisectors here would also be equidistant, and they're not, meaning that this side length here should be the same as this length here. Like it would have to be in the midpoint, but you can see that this is shorter than this one. So that means that this must be a kite, and kites have the following properties. I'm going to draw a more exaggerated kite so you can kind of understand. Okay, well, more or less, right? If you have a kite like this side would be congruent to this side, and this side would be congruent to this side. So therefore, and this is the same orientation, right? Because you can see that this is the shorter end and this is the longer end. So this side has to be congruent to this side. So 3a plus 2 has to equal to 5a minus 8. And then this side would have to be congruent to this side. So that would give me the equation 2a plus 4 has to equal to 2x minus 4. Now, in order for me to figure out x, I first need to figure out a, and that's why I wrote this equation first. So we're going to solve for a, and then we plug it in and solve for x. So I'm going to subtract this 5a. So negative 2a plus 2 is equal to negative 8. Subtract the negative 2. So negative 2a is equal to negative 10. And then divide the negative 2. And we get that a is equal to 5. So now I'm going to plug in the 5. So 2 times 5 plus 4 is equal to 2x minus 4. This here is 10. 10 plus 4 is 14. Add the 4 to both sides. So we get 18 is equal to 2x. And then divide the 2. So we get that x is equal to 9, which I had already done before I started recording. So it's already selected. So B, 9. Let's move on to the next. A student is working in a geometric construction. AD is drawn. What geometric construction is shown? So from here, you can see that these two arcs were made, and we would have to connect point A to point D. And if you do that, this is an angle bisector, because this is what the construction of an angle bisector is, where you would draw an arc, and then you put your compass point here, and then draw the arc. Well, you would measure this length, put your compass point here, and then draw an arc, and then keep the same distance, put the compass point here, draw another arc, and then connect point A to that one, and that is your angle bisector. If these lines here are parallel, find the value of x. So these are alternate interior angles, and alternate interior angles are congruent. So we would make those two equations there equal to each other. So 2x minus 10 is equal to 65 minus x. So I'm going to add this x over, and we get 3x minus 10 is equal to 65. Add the 10. So 3x is equal to 75. Divide 3. We get x is equal to 25. Okay, in this one, these are alternate interior angles, and alternate interior angles should always add up to 180. So these are the only ones on parallel lines that are not congruent but just add to 180. So we're going to get those two expressions there, 3x minus 10, and we're going to add them together, plus 5x plus 30, oops, and we make it equal to 180. And that's how we can solve for x. 3x plus 5x is 8x, plus negative 10 plus 30 is 20, equals to 180. Subtract the 20. We get 8x is equal to 160. Divide the 8. So x is equal to 20. Okay, here we're matching. So corresponding angles are over here. I'm going to draw some pictures here so you understand. So we have these parallel lines, pretend those are parallel, and a transversal. So corresponding angles are angles that land on the same side of the transversal and on the same side of the parallel lines, or rather like the same orientation. So this is on the right of the transversal above the parallel line, the right of the transversal above the parallel line. Now, alternate interior angles, alternate means opposite, interior inside of the parallel lines. So alternate interior angles, an example would be like this one here and this one here. those would be alternate interior. Or this one here and this one here. These would also be alternate interior angles. Same side interior angles would be also on the same side of the transversal and on the inside. So that would be like this here and this here. And these are the ones that add up to 180. See how they're on the same side? Sorry. And on the interior of those parallel lines. And then congruent triangles are obviously triangles that all have same sides and angles. So here we go. Pairs of angles formed by two lines and a transversal that make a Z pattern. So let's see, which one forms a Z pattern. So let's see, a Z would be like this, like that, and like that. So this angle and this angle. So that would be alternate interior. Let's start a fresh drawing here. Okay, the next one is pairs of angles by two lines and a transversal that form an F pattern. So let me see. An F pattern would be something like this. So that would be this angle with this angle. Those would be corresponding. Triangles in which corresponding parts, sides, and angles are equal in measure, those are the congruent triangles. And finally, pairs of angles formed by two lines and a transversal that make a C pattern. Even though we know this is same side interior, I'm going to show you how that would have worked out. If we have here our two parallel lines form a C pattern, that would be like this. So that would be this angle and this angle, which are on the same side. All right, for this one, we have a bunch of terms and then the diagram. So we're going to see if we can match these. Now, here we have what looks like two angles that are directly next to each other. I don't know if they're the same. So I'm going to go ahead by looking at all of these options here. The only one that kind of looks like it would be, because these are all angles, hypotenuse leg, triangles, hypotenuse, transversal, for adjacent angles. Adjacent angles are angles that share a side, which would be that BO. So this is adjacent angles. Here we have two parallel lines and a transversal. And if you look at all of these options here, the only one that kind of makes sense would be transversal. Go in there. Okay. Now here we have this red line there, and then it's cutting the angle in half. So that must mean that it is an angle bisector, since that's what angle bisectors do. They cut the angles in half. Now here we have what looks like to be two congruent triangles, since here there's an angle, here's the same angle, then a side, the same angle, and the same angle. So this is angle, side, angle. So these must be congruent triangles. This is difficult. Okay. Oh, or I guess angle, side, angle congruence would be more likely because this is more specific. So angle, side, angle, we're going to go with that one. Now here, you have here, this is an equilateral triangle since all of the angles here have the same angle. They're all 60 degrees. And if the angles are all the same, the side lengths are also all the same. So this is an equilateral triangle. All right, this is a right triangle, and you see that we have the legs here are the same. So this must be the hypotenuse leg. Let's see. Yep, hypotenuse leg. So that is a way of proving that right triangles are congruent. If the legs are the same and the hypotenuse is also the same, then this would be hypotenuse leg. Oh, I put equilateral. Sorry, I can see here that it's also equal angular. So equal angular means equal angle. So I'm going to change that over here. And then I'm going to put this one under hypotenuse-like. Okay. Here we have these two triangles. We have equal side, equal angle, equal side. This is side, angle, side. So we're going to go down to side, angle, side congruence. There we go. Now for this one, we have all angles are congruent, all sides are congruent. These are congruent triangles. Let's see, where is it? Oh, there it is. Now here we have angle, angle, side, angle, angle, side. So that is the AAS congruence. Okay, these are vertical angles. So if you ever have two lines that form like an X, the angles that are directly across from each other are congruent. So vertical angles. This one's the easiest one to recognize because you have all three sides are congruent. So this is side, side, side congruence. What a pain. Okay, I have just a couple more here. Here we have just a right triangle. We're missing the hypotenuse. This must mean that this is for the hypotenuse, since the hypotenuse is the diagonal of a right triangle. And finally, equilateral, and that is a triangle that has all equal sides. So equilateral. Now, equilateral and equiangular, they're basically the same thing because an equiangular triangle is also equilateral, but this is to be more specific. All right. Oh my goodness. Okay, let's see what we got here. Just scanning all of these terms. Okay, let's see what we can do. The fact that if you know the congruence of two angles and their shared side, then you know that the two triangles are themselves congruent. So this is two angles and a shared side. So this would be, let's see, two angles and a shared side. That would be, probably angle, side, angle, or angle, angle, side, but it's a shared side. So I'm going to come back to that one. The side opposite the right angle in a right triangle, that is the hypotenuse. The hypotenuse is always opposite of the right angle. A line drawn in a figure to aid in a proof. So if you're aiding, that means you're helping, and the word auxiliary means to help. So this is an auxiliary line. A triangle with at least two congruent sides. That would have to be at least two congruent sides. Well, it could be side, 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 or side, angle, side, since that's also at least two. We'll come back to that one and see. A statement usually in the form if then. This would be a hypothesis. And that we learn in science, right? When you're writing a hypothesis, it's always an if then statement. Can this go there? Okay. An angle formed by two sides of a polygon with a common vertex. Let's see, an angle formed by two sides of a polygon with a common vertex. Let's see. That would have to be, is that inside of a polygon? By two sides of a polygon. I have a feeling that is an interior angle, but we'll come back to that one as well, just to make sure. Let's see, an angle formed by one side of a polygon and the extension of an adjacent side. So if you're extending, that's like, think about it like this. if you have, let's say this pentagon, if I extend this side, this is the exterior angle. So it is an exterior angle. Okay. A triangle with three congruent sides, that would have to be an equilateral triangle, three congruent sides. An angle formed by two sides of a, I'm pretty sure it's an interior angle, but again, I'm going to come back to that one after. The shared side of two adjacent and congruent angles, it is a line, ray, or line segment. Let's see. The shared side of two adjacent and congruent angles. So this would have to be an angle bisector, because if it is adjacent and the line cuts that angle in half because they are congruent, it must mean it's an angle bisector. Okay. A sequence of statements, one statement following logically from the previous that shows a conclusion must be true whenever the hypothesis is true. This is one statement following logically from the previous. This would be a proof. The fact that if you know the congruence of an angle and its two sides to another angle and its two sides in a different triangle, then you know that the two triangles are congruent. So two sides and an angle. So this must mean, two sides to another angle. So two sides to another angle. So that must mean it's SAS, two sides and an angle. Sorry, I have lots of other things open. I don't know why this popped up. Okay, let's see. Two angles that share a side and their vertex. Those are adjacent angles because they share a side and a vertex. So adjacent angles, which was up here. A proof in which the statement to be proved is assumed to be false and a contradiction is shown. Let's see, an indirect proof. That's what that would be. An indirect proof is where you can prove something by contradiction. So we'll put that there. Given a conditional statement, the hypothesis of the conditional statement is the first portion before the then. The hypothesis is the first portion before the then. The then is the conclusion. So I'm going to go with conclusion. A triangle with three congruent angles, that would be an equiangular triangle. Let's see. A line that intersects at least two other lines, that is a transversal. The non-adjacent angles formed by two intersecting lines, those are vertical angles, because if two lines are intersecting, right? Again, let me draw you a picture. The ones that are not adjacent would be this and this. So if they're not adjacent, it would be this one and this one, which would be those vertical angles. The sum of the lengths of any two sides of a triangle is greater than the length of the third side. That is the triangle inequality theorem, which I think is down here. Yep. So again, you use the words to kind of help you, right? Greater than is an inequality, so inequality theorem. Given a conditional statement, the conclusion of the conditional statement is the second portion after the then. Oh, okay, so let me change this. A hypothesis is the if part. A conditional statement is the if then. So given a conditional statement, it is the portion before the conclusion, so that's your hypothesis. The fact that if you know the congruence of two angles and an unshared side, then you know the two triangles are themselves congruent. So, okay, Unshared side would be the side that is after the two angles. So this would be the angle side. So that means that the other one, the one with the shared side, that is the angle side angle. Okay? The fact that if you know three sides of two triangles are congruent, then you know the triangles are congruent. That is side, 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 because you have three congruent sides. An angle formed, okay, I'll come back to that one. All six pairs of corresponding parts are congruent, three pairs of both sides and angles. So those are just congruent triangles. What's left? Hypotenuse leg, isosceles. Oh, isosceles. I didn't see that one. A triangle with at least two congruent sides. That's an isosceles triangle. An angle formed by two sides, that must be the interior angle, as I mentioned. And last one here, the fact that if you know the congruence of the hypotenuse and one side of the two triangles, that must mean that the triangles are congruent. That is your hypotenuse leg. Okay? Oh my God. All right, here we go. A point that lie on the same line. Those are collinear because it's co, like together, and linear, on the same line. Consists of two endpoints and all the points between them. That is a line segment. A segment only has two endpoints. Lines in the same plane that do not intersect. Those are parallel lines. Parallel lines never intersect. Has two dimensions extending without end. It is often represented by a parallelogram. That is a plane. Think of like a sheet of paper. Has one endpoint and extends without end in one direction. That's a ray. Divides a segment into two congruent segments. So that would be a midpoint, because a midpoint would be in the middle, and then that segment would be cut in half. The common endpoint of two or more rays or line segments. The common endpoint of two or more rays or line segments. Let's see. We'll come back to that one and see. One of the two rays that form an angle, that would be the side of the angle. Points that lie in the same plane are coplanar. Same concept as collinear, but on the same plane. The common endpoint of two or more rays or line segments. Oh, that's a vertex. I just realized that. That's the vertex. Think of like the vertex of an angle. That's where the two rays connect. Lines that intersect at 90-degree angles, that would be perpendicular lines. It has no dimension. It is a location on a plane. It is represented by a dot. That's a point. A figure forms by two rays with a common endpoint. That is an angle. Angles are made by two rays. Has one dimension, is an infinite set of points represented by a line with two arrowheads that extend without end, and that is a line. The vertices of triangle JKL have coordinates blah blah blah. Under which transformation is JKL not congruent? The only type of transformation that would make any figure not congruent is a dilation. A translation, a rotation, and a reflection are all rigid transformations, meaning that it does not change the size or the shape of your figure. But dilations change the size, making it not congruent. So that would be D. A triangle with vertices, blah, 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 is reflected across the line y is equal to -2. What are the vertices of the image? Okay, so I'm going to pull up a figure here. We're going to draw it out. Okay, so I'm going to just get a graph. I like to work with graphs. So let me see how, all right. Yeah, we'll use this one here. Let's make this a little smaller so you can see it. Okay, here we go. So we have the points -3, 1, 1, 5, and 4, 1. And this is my triangle. Okay. And we are going to reflect it along the line. Let me see. Y is equal to -2. So we can draw this line out, right? Y is equal to -2 is a horizontal line because it goes through the y-axis. That's why it's called y equals -2. When we reflect, we're going to move these points over to the other side. So what we do is we count 1, 2, 3. So 3 units below. 1, 2, 3. Then this one is 1, 2, 3, 4, 5, 6, 7. So I need to count 7. Now I don't have enough space, but I can write the coordinate. 1, 2, 3, and then this is, okay, 1. Let me see a second. Okay, let's do this. Oops. See if I can make it. Oh, perfect. Okay. So this is 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. Okay, and then this is 1, 2, 3. 1, 2, 3. Okay, so these coordinates, let's make sure we write that out. This is 1, 2, 3, 1, 2, 3, 4, 5. So -3, -5. Then this is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, -9. And then 4, 1, 2, 3, 1, 2, oh, 1, 2, 3, 4, 5, -5. So those would be my 3 points. I like to draw them out. I think it's easier for me to understand, so that's why I do them. Okay, so -3, -1, which was this one, will give me the point -3, -5. Then 1, 5 gave me the point, that's this one here, 1, -9. And then 4, 1, the x didn't change, and it's the same as the other, -5. Select the values that correctly completes the sentence about the symmetry of a regular pentagon. A regular pentagon has, let's see what it says, lines of symmetry and has, okay, so let's see. Let's draw out a pentagon. Do I have shapes here? No. Okay, that's okay. I don't know what a regular pentagon just basically means that all sides are equal, so we're going to pretend these are all equal sides. So for lines of symmetry, let's actually use this here. Okay, we have this line, we have this line, this line. Basically, it goes through all of the vertices. So we have 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4. We have 5 lines of symmetry. And has, now to figure out the rotational symmetry, what we do is we take out this pentagon, and we need to figure out how many angles, or rather with the sum of all the angles for a regular pentagon, and then we need to divide it by 5. So let's figure that out. Sorry, I misspoke. So to figure out the rotational symmetry, any polygon in rotation, one full rotation, I'm sorry, is 360 degrees. We have 5 sides, so we divide that by 5, which gives us 72. So the rotational symmetry is 72 degrees. Which figure always has exactly 4 lines of reflection that map the figure onto itself? So let's see, a square, let's start off with a square. We have this, we have this, we have this one here, and this one here. So I'm pretty confident saying it's a square, since a rectangle would just have this one and this one, so only 2, because the diagonals would not cut it in half. And octagons and equilateral triangles have more, so a square. Which regular polygon has a minimum rotation of 45 degrees to carry the polygon onto itself? So we know that a pentagon is 72, so it's not that one. A nonagon has 9 sides, so we would do 360 divided by 9. Let's see if that works. Actually, I don't need this right now. Goodness. Let's see if I have my calculator here. Okay. Okay, let's see, 360 divided by 9 is 40, so no. A decagon has 10, so 360 divided by 10 is 36. An octagon has 8, so 360 divided by 8 is 45, so an octagon. The figure shows 2 perpendicular lines, S and R, intersecting at point P in the interior of a trapezoid. Line R is parallel to the bases and bisects both legs of the trapezoid. Line S bisects both bases of the trapezoid. Which transformation will always carry the figure onto itself? A reflection aligned line R. That would mean that it would turn upside down and it would not look the same, so no. A reflection across line S. Well, line S bisects this side, and then if you flip it over, it would look the same. So I'm going to go with a reflection across line S. A rotation of 90 degrees would just turn it lengthwise, so no. And a rotation of 180 would make it upside down, so also no. So yeah, confident would be. Okay. A regular pentagon is centered about the origin and has a vertex at 0, 4. Which transformation maps the pentagon to itself? A reflection across line M would not be right because then it would be upside down. A reflection across the x-axis will also make it upside down, so no. A clockwise rotation of 100 degrees about the origin and a clockwise rotation of 144 degrees about the origin. Okay, so we know that a pentagon has rotational symmetry of 72 degrees. So if it rotates every 72 degrees, it will look identical. So 72 plus 72 is actually 144. So that means that it would be D, because it would have rotated twice. Okay, for this one it says a triangle is shown on the coordinate grid. The black triangle is the pre-image and the red triangle is the image of the transformation. Which of the following show the correct algebraic rule? So you can see here that the black goes to the red since the black is the pre-image. So this means it had to have moved. Now what you do is you compare one point with the other. So it moved 1, 2, 3, 4 units to the left and then 1, 2, 3 units up. So that means it would have to be x minus 4, y plus 3, because it went to the left 4 and it went up 3. If JKL is rotated 90 degrees about the origin and then translated using this rule, what are the coordinates of the final image of point L? Okay, so L seems to be located, this is going by 2's, so 2, 4, 5, negative 1. So let's see what we can do here. So that is our original point, xy. 5, negative 1. Now, a reflection of 90 degrees is this rule, negative y, x. And then it followed the translation rule afterwards of x minus 8, y plus 5. So we just apply these rules to the points. So if it went from 5, negative 1, and then the rotation of negative yx, then that means that these switch places and that number will become positive, and this is 5. And then we subtract 8, so 1 minus 8 is negative 7, and 5 plus 5 is 10. So negative 7, 10. Point F prime is the image when point F is reflected over the line x is equal to negative 2 and then over the line y is equal to 3. The location of F prime is 3, 7. Which of the following is the location of point F? Okay, I'm just going to draw a picture. So I'm going to go back here to my graph that I had done. Let's clear this out. Okay. So the final point is 3, 7. Let me get a bigger graph because this doesn't have enough coordinates. Okay, so 3, 7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So we're working backwards. It was reflected over x minus 2 and then over y is equal to 3. Sorry, x is equal to negative 2. So we're going to reflect along y is equal to 3 first. So remember, because we're going backwards because we want the pre-image. So we're going to do the y is equal to 3 first, and then the x is equal to negative 2. So y is equal to 3 is that horizontal line because it goes through the y-axis. So this point is 1, 2, 3, 4 units away. So 4 units the other way. 1, 2, 3, 4. And then it was reflected, well, firstly, it was reflected along x is equal to negative 2, which is this vertical line because it goes through the x-axis. So 1, 2, 3, 4, 5. So now I'm going to count 5. 1, 2, 3, I can count, 4, 5. So over here. So this is the point 1, 2, 3, 4, 5, 6, 7, negative 7, negative 1. Point P is located 4, 8 on the coordinate plane. Point P will be reflected over the x-axis. What will be the coordinates of the image of point P? If it's reflected over the x-axis, the rule is x comma negative y. So the only thing that changes signs is the y. So 4, negative 8. The point negative 7, 4 is reflected over the line x is equal to negative 3. Then the resulting point is reflected over the line y is equal to x. What is the point located after both reflections? So here we have those two lines. This is x is equal to negative 3. So we count 1, 2, 3, 4 units away. So I'm going to go 4 units the other way. 1, 2, 3, 4. So right here. Then it's reflected across the line y is equal to x. So this is the point 1, 4. So when it's reflected along y is equal to x, what happens is the x and the y, they switch places. So if the point is 1, 4, then that reflection would be 4, 1. And you can kind of see that here because if you reflect, it would be across this square and then this half. So here's the half and then here's the square. And this is the point 4, 1. Which transformation on quadrilateral ABCD produces an image that does not preserve distance between points in quadrilateral ABCD? What this means, preserving distance, is that the shape did not change, obviously, and did not change size. So again, another example of when the figure would not be congruent. And the only time the figure is not congruent is after a dilation. Match each of the 3 written descriptions of a transformation with the algebraic rule. Okay, translate 3 units to the right and 2 units up. So that would mean x plus 3, y plus 2. Translate 4 units to the left and 2 units down. So x minus 4, y minus 2. Reflect across the y-axis, and that means that the x will change signs. So that's the negative x, y. Rotate 180 degrees about the origin. Both the x and the y would change signs. So that's the x, y, negative x, negative y. And these are all rules that were probably given to you and you would need to remember. Okay, more vocabulary. All right. A figure that can be rotated about a point by an angle less than 360 degrees so that the image coincides with the pre-image has rotational symmetry. So that could be a center of rotation. I'm not sure. There could be a couple things, so I'm going to leave that one for now. A transformation across a line called the line of reflection. So the line of reflection is a perpendicular bisector of each segment joining a point and its image. So that is a reflection. The point around which a figure is rotated, that is the center of rotation. A transformation in which all the points of a figure move the same distance in the same direction. The figure is moved along a vector so that all the segments joining a point and its image are congruent and parallel. This is a translation. A vector is basically the direction in which that it is moving, so translation. The transformation of a figure such that the image coincides with the pre-image, the image and pre-image have symmetry. So this would be a rigid motion because if it coincides with the pre-image, then that means that it is congruent. So that must mean it's a rigid motion. A transformation about a point P, also known as the center of rotation, such that each point and its image are the same distance from P, all the angles, blah, blah, blah. This is a rotation. If it's a transformation that's going around a point, rotation. A change in the position, size, or shape of a figure. A transformation maps the pre-image to the image. Or shape. Oh, this is a transformation. A line that divides a place figure into two congruent reflected halves. This would be the line of symmetry. A transformation of the plane or space which preserves distance and angles. Oh no, that is a rigid motion. Sorry. This is the rigid motion. Preserves distance and angles. The transformation figures such that, that have symmetry. So a transformation of figures such that the image coincides. I think this would be rotational symmetry. Or the transformation of figures such that the image, a figure that can be rotated about a point by an angle less, this is rotational symmetry. So this must be symmetry. The wording was a little strange. Okay. A portion of a line consisting of 2 points and all points between them, that is a line segment. These are kind of repetitive from what we did earlier, so they should be easier. A connected straight path, it has no thickness and it continues forever in both directions. That's a line. Anything that continues forever would be a line. A figure formed by 2 rays with the same endpoint, that's an angle. The set of all points in a plane that are fixed distance from a point called the center. That's a circle. A portion of a line that starts at a point and continues forever in one direction. That's a ray. Lines that intersect at right angles are perpendicular lines. A specific location, it has no dimension, represented by a dot, is a point, and lines that lie in the same plane and do not intersect are parallel. 2 lines that never intersect and have the same slope are parallel lines. A blank has a starting point and no stopping point. That's a ray. Define the figure below since it has two endpoints. This is a ray. Okay, that's it. Let's submit. Ooh, something was wrong. Let's see what that was. Ugh, these. Okay, so given a conditional statement, the conclusion of the conditional statement is the portion. Oh, I guess I misunderstood. So these would just be the opposites. Okay, but that's it. How do I stop this here?